All right, welcome to The Explainer. Today, we are setting off on this absolutely incredible investigative journey into the unseen depths of our very own planet. I mean, think about it. We live our entire lives right here on the surface of the Earth. Yet, for centuries, what lies beneath our feet has been one of the biggest mysteries in human history. And it's an important one, too, because this massive hidden engine beneath us drives literally everything, from earthquakes to the magnetic field that keeps our atmosphere in place. So we're going to break down the science, the clues, and the brilliant deductions that have allowed geologists to map the inside of the Earth, all without ever actually seeing it.
So here is the core mystery we're unraveling today. The radius of the Earth, so from the surface all the way down to the very center, is roughly 6,378 kilometers. But get this. The deepest hole humanity has ever managed to drill is up in the Kola Peninsula in the Arctic, and it reached a depth of just 12 kilometers. 12? We have literally just scratched the surface. So if we can't physically reach anywhere near the center, how on earth do we know what's actually down there?
Okay, let's dive into this. Here is our roadmap to solving this huge geological mystery. We'll look at the investigation itself, our important sources of information, seismic clues, the chemical layers, and finally, our modern understanding of the Earth's zones.
Starting off with Part 1, the investigation, how we map the unseen.
First off, we've got to acknowledge the incredible challenge scientists are up against here. Trying to map an interior that you can never physically see or touch, that takes some serious ingenuity. Because the very first major roadblock you hit is extreme heat. It's called the geothermal gradient, and it basically proves that it gets ridiculously hot ridiculously fast as you go down. At first, for every 32 meters you descend, the temperature goes up by a full degree Celsius. By the time you're 100 kilometers down, it's jumping 12 degrees for every single kilometer. This immense heat, which is mostly driven by radioactive materials and intense gravity in the core, creates a literal absolute barrier. Direct human exploration is just not happening.
So that brings us to Part 2, important sources of information, where we look at the indirect data. Because we can't just, dig a super deep hole, we have to rely on indirect or unnatural sources to build our theories. Back in the day, early scientists were completely stuck. They were basically making wild guesses about the inside of the Earth based on how they thought the planet formed, and it just led to total chaos. T.C. Chamberlain thought the Earth formed from solid particles, so he said, okay, the core must be solid. James Jeans thought it cooled from a liquid, so he assumed a liquid interior. And Laplace, he argued for a gaseous origin. With all these totally conflicting ideas, early science was pretty much at a standstill. No one actually knew.
Now, we do have some direct, natural clues, like volcanic eruptions. When a volcano blows, it spews out liquid magma, which absolutely proves that at least some part of the Earth's interior is in this molten liquid state. But here is the catch. The pressure deep inside the Earth is so incredibly intense that rocks simply cannot stay in that same molten state the further down you go. So while volcanic magma is a fantastic clue, it's ultimately a pretty limited window into what's actually happening in the deep interior.
All right, Part 3, the mystery of seismic waves. This is our ultimate geological X-ray machine. This is where the investigation gets truly fascinating. Seismology, which is the study of earthquake waves, acts as that X-ray machine for us. When an earthquake hits, it sends these massive shock waves ripping through the entire planet. So, the crucial point here is understanding the difference between the two main types of waves, P waves and S waves. P waves, or primary waves, are kind of like sound waves. They're crazy fast, and they can travel through anything, solids, liquids, gases, you name it. But S waves, secondary waves, are totally different. They can only travel through solid rock. If they hit a liquid, boom, they just completely disappear. Keep that rule in the back of your mind, because it's the ultimate key to unlocking the Earth's core. Moving to Part 4, chemical makeup, the Siao, Sima, and Nife layers.
So way before we had these modern seismic X-rays, geologists had to categorize the Earth by its chemistry. In 1903, this brilliant Australian geologist named Edward Suess proposed a really foundational model. He divided the planet into 3 distinct chemical layers based on weight and density. It's kind of like a giant layered cake where all the heaviest ingredients just sink right to the bottom before it bakes, right? The topmost layer is Sial, made of silica and aluminum, which forms our lighter granite rocks. Below that is Sima, silica and magnesium, which gives us heavier basalt rocks. And finally, sinking all the way down to the very center thanks to gravity is Nife. This is a super dense, incredibly heavy core made entirely out of nickel and iron.
Which brings us to Part 5, modern zones. Let's look at the actual seismic mapping. Now, what's really interesting about this slide is that today, thanks to the International Union of Geodesy and Geophysics, we don't have to just rely on chemical guesswork anymore. We have a highly detailed model that's based entirely on how those seismic waves change their speed as they blast through the Earth. By pinpointing the exact moments where those P waves and S waves suddenly speed up, or slow down, or just disappear entirely, our seismic detective tools gave us a direct blueprint of 3 major physical zones: the crust, the mantle, and the core.
So let's start right up at the surface with the crust. This is the solid outer shell that you and I are sitting on right now, and it is surprisingly thin. If you imagine the Earth as an apple, the crust is actually thinner than the apple's skin. Under the oceans, it's only about 5 kilometers thick. Under our continents, it averages about 30 kilometers, but if you go beneath massive mountain ranges, it can plunge down to about 100 kilometers deep. And even within the super thin crust, there's a boundary, the Conrad discontinuity, that actually separates the lighter upper crust from a denser lower crust.
And if we look at what this crust is actually made of, the numbers may totally surprise you. You might assume it's mostly carbon, or maybe iron, right? But by weight, oxygen makes up a staggering 45.2% of the Earth's crust. Silicon comes in second at 27.2%, followed by aluminium and then iron. So oxygen and silicon just absolutely dominate the chemical makeup of the ground we walk on.
Okay, so right beneath that thin crust lies the mantle. And to really grasp the mantle, you honestly just need to look at this one single massive number, 83%. The mantle takes up 83% of the Earth's entire volume. It also holds 68% of the planet's total mass. It is literally the absolute bulk of our world.
So the mantle begins right below the crust, at a specific boundary known as the Moho discontinuity. We actually discovered this back in 1909, when seismic waves suddenly sped up, which basically told us, hey, we just hit some much denser rock down here. The mantle extends all the way down to 2,900 kilometers. But what's really wild is that between 100 and 200 kilometers down, those seismic waves actually slow down temporarily. We call this the zone of low velocity. It's kind of a slushy area, before the waves speed right back up as they travel even deeper.
Then, at exactly 2,900 kilometers deep, we hit a massive geological wall, the Gutenberg discontinuity. Right at this line, the density of the rocks suddenly doubles, and those P waves, they rocket up to a blazing 13.6 kilometers per second. This huge dramatic jump is the planet's way of signaling that we have finally left the rocky mantle and we've officially entered the core.
Now, remember that vital X-ray rule we established earlier about S-waves? The rule that they totally disappear the second they hit liquid? Well, right here at this 2,900 kilometer mark, the S-waves just vanish completely. They absolutely cannot pass through. And this right here gave scientists undeniable concrete proof that the outer core, which stretches from 2,900 down to 5,150 kilometers, is entirely liquid. No guessing required.
But for sure, the deepest, craziest mystery lies even further down, at 5,150 kilometers. Separated by what we call the Lehman discontinuity, we hit the inner core. And this brilliantly illustrates the sheer, mind-boggling power of planetary physics. Despite the unimaginable heat down there, the physical pressure is so incredibly crushing that the nickel and iron are actually forced right back into a solid state. The density hits an extreme 13.6 grams per cubic centimeter. And those P waves, they just zip right through this solid metal heart of the planet at incredible speed.
So if you ever need a quick cheat sheet to remember the architecture of the Earth, just memorize these 5 specific seismic checkpoints from top to bottom. Ready? The Conrad splits the crust. The Moho separates the crust from the mantle. The Ripetti divides the upper and lower mantle. The Gutenberg plunges us right into that liquid outer core. And finally, the Lehman marks the boundary of the solid iron inner core.
It's just wild to think about. We've only physically dug 12 kilometers down, yet by using earthquakes, math, and physics, we've accurately mapped a world that is over 6,000 kilometers deep. I mean, it really shows the incredible power of human deduction, but it also leaves us wondering, as our seismic technology and our computer modeling continues to evolve, what completely new, totally unseen mysteries might we discover next, hiding quietly right beneath our feet? Thanks so much for joining me on this explainer. Keep asking those big questions, and I'll see you next time.